Hello everyone and welcome to episode 10 of CS350 Online. I'm your host as always, Leslie Eisted. On today's episode, we're going to continue our discussion of how processes work in our operating system. In particular, we're going to be focusing on how we bridge the gap between unprivileged code and privileged code. But first, let's talk about our OS of the day. So, the OS of the day is called PIC. And PIC was developed starting around 1965 and officially released commercially in 1973. It was developed by a gentleman by the name of Dick Pick, for whom it is named. And what's really interesting about the PIC operating system is just how different it is from all of the other operating systems at the time. And furthermore, what's kind of neat about it is it's said to be Unix's major competition by the 1980s. Now, what makes the PIC operating system so unique and so different from everybody else is the fact that it was based on database transactions. So they use hash-based databases for quick retrieval of things like files and records. And that actually led to them being able to do some very interesting tasks. Particularly, you can imagine that companies who are interested in employee and inventory management, a database-based operating system would probably be a pretty ideal thing, having that transactional language actually built right into the operating system. So they offered a query language, they also had a procedural language and a compiled basic language, so you could actually write regular programs for this OS. And it did all of the expected things, like you could manage your peripherals, attaching different hardware. It supported multiple users, and it offered time-sharing concurrency. So you could actually have multiple users using the machine at the same time, which is pretty cool. Now, the other thing that it did was demand paged virtual memory, which is a pretty big deal at the time. So this was a full-blown operating system, and it was a monolithic kernel. That is, everything in the kitchen sink was actually included into the kernel. Now, what's interesting about this particular operating system is that it's actually still in use today, although not in an operating system form. So at some point, they realized that in OS, this was not succeeding, and they moved it to just being a database program that you can install on top of Windows. And I believe now they're looking at solutions for cloud computing, so adding extra security on top of things like Google Cloud and so on and so forth. So this place is actually still around, which is kind of neat. Okay. So what did we do last episode? So on our last episode, we actually introduced to you the concept of processes. And I want to kind of disambiguate that from the concept of a program. Now, we've always thought of the world as programs. I'm running a program. But in the operating system, you are creating a process. And what the process is an execution environment that the operating system is creating for that program to run in. And it includes things like the address space, the array of threads. It also is going to contain things like the file descriptor table and any connections to different pieces of hardware resources that that particular program is going to need. So the process is actually this whole environment. Now, processes, we uniquely identify them not by the name of the program that is running, but we're actually going to use a unique identifying integer. Now, you may note, if you've opened up OS 161, that the process structure is missing that unique identifying integer, and that's because we're leaving it up to you to decide how to implement that. Remember, though, that no two processes can have the same PID, because otherwise we wouldn't be able to differentiate them from each other. Another thing to keep in mind is that when would you actually be able to reuse a process ID number? Because obviously computers can run for very long periods of time, mostly, and that's going to mean that at some point you could run out of integers to assign to your processes. So at what point can you reuse those PIDs? It's just something to think about. Now, we talked about some of the different process management calls that we have available to us. I'm just going to bring that up here. We have things like fork and exec-v, which fork, if you recall, is going to create a brand new process, which is an identical clone of the parent. Now, it's an identical clone in terms of its address space and what the program is running, the program counter, the stacks, and so on. But it is actually a separate process structure, and it does have its own PID. execv, on the other hand, is simply going to change the program that the existing process is running. So we're not creating any new processes. We are just changing the program that you're running. And that's going to involve is destroying the old address space, which contains all of the stacks and heaps and code for the old program, and creating a new address space and loading the new program into it, and then setting the program counter to point to the entry point instruction of the new program. So that's execv. Now, an interesting thing with execv is to recall that parent-child relationships are actually preserved through execv. So you can't, no matter how many times you change your hair color, you absolutely cannot change who your parent is. Then we have exit, which is going to terminate the calling process. And exit lets us pass an exit status code with it. Now, this is a little bit of information that we can leave around for our parent to let them know if we completed successfully or unsuccessfully, and perhaps why. Typically speaking, if you pass 0, that usually means that you terminated successfully. And if you pass a value that is not 0, that typically means you did not succeed. Now, that does not mean that if you are using this exit function that you have to use the exit status codes like that. It's simply stating that that is how they are typically used. Then we have wait PID, which works alongside of exit, and wait PID is going to let one process wait for another process to terminate. And then once the other process is terminated, the process which called wait PID is permitted to extract the exit status code and the exit code from the terminated process to do whatever it needs with it. And what we use this wait PID for is actually synchronization between processes. And the example that I like to use is actually MapReduce, because many MapReduce implementations are actually multiple processes. Well, you're going to have one kind of master controlling process that's going to fork off all those map workers. And we can't actually issue the reduce phase until the map workers have actually started to complete. So we need a function like wait PID to permit synchronization between separate processes. And that's what we're going to get. Now, there are some caveats with wait PID. For one, you're only allowed to call wait PID on your child's process. So if you call wait PID and you pass it a PID that does not correspond to one of your children, then wait PID is not going to succeed. Now, the other thing to keep in mind is once you've called wait PID on a child once, you've already conducted the autopsy, you know why they terminated. That's kind of going to signal the operating system that they can safely get rid of the child zombie. And you cannot then call wait PID on the same PID back to back. That would not be good. And then, of course, we have get PID, which simply returns the PID of the process that called it. So those are our process management calls. And none of these are implemented in OS 161 yet. Now, that's kind of a strange thing to say because the user side of these is actually implemented. But what is not implemented is the actual internal kernel implementations. And the reason they're not implemented, of course, is because that's going to be your assignment A2A and A2B. All right. Now, one of the other things we talked about is the fact that we're going to be using our processes here, or not our processes. We're going to want to isolate our user programs completely from the kernel. And this comes down to, let's suppose you had a user program, and that user program did have access to the kernel's data structures, and it did have access to the kernel's API. Then what you're going to end up having is a situation where a user application can see the kernel's data structure. And we don't necessarily want that to happen because it poses an interesting security breach, or at least it makes it easier. The other fundamental problem with letting user applications have direct access to the kernel is the fact that if we try to patch the kernel for a security bug or other reason, and we change the data structure, then we also have to go back and change the user application. Or we have to keep supporting legacy versions of the data structure and the function, which may have been the reason for the security breach in the first place. So as a matter of both security and good abstract design, we don't want our user applications having any access to the kernel's data structures or its internal functions whatsoever. And we're actually going to separate them on a more fundamental level. In particular, we introduce at the CPU two different modes of execution, unprivileged and privileged. Now, if you're running a modern CPU, you actually have more levels of privilege than that. You usually actually have 4 levels of privilege. Although, unless you are running a VM, you're probably only using 2 of them. So unprivileged code is actually a mode on your CPU that's going to prevent user code from executing certain kinds of instructions and accessing certain regions of memory. And we'll talk more about the memory bit when we talk about virtual memory. The other thing that we have is when we flip into privilege mode, then we would be able to access everything. So the idea being that a user program is going to be stopped at the CPU level from getting into places it shouldn't be permitted. Now, of course, if you've done any reading about Meltdown or Spectre, you know that there was a pretty big security flaw that actually let people bypass this little bit of security and get access to privileged data in the cache on Intel CPUs. And again, I know I promised I would post the paper. I haven't gotten to it, but I will post it. So now we have this problem here of our user application needs the kernel to save a file. How are we, the user application, going to get the kernel to save a file, who's the only person who is allowed to actually talk to the hardware, if we can't actually call any of the kernel's functions? How do we, the user program, actually force the kernel to run any code if we can't call its functions directly? And that's what we're going to focus on today, is how that works exactly. And we're going to actually dive into some of the OS 161 code so that you can see at least how it works in OS 161. And if you are sitting there saying, this seems incredibly inefficient, why don't we just give it access? And it's like, yes, it is inefficient. And yes, there are operating systems that give you direct access to the kernel. One that comes across top of my head is Temple OS. Gives you, well, there's no separation between user and kernel. So it's a little bit more efficient, but there's also no security here. All right. So let's continue then talking about that. And there are 2 ways that we do know for certain that we can force kernel code to run. The first way is through interrupts, which are electrical signals that are raised by the hardware to indicate that they've done something. So that's like saying I pushed a button on my mouse, and that's going to raise an electrical signal, and that's going to cause us to actually run the kernel code. And why is it going to cause us to run kernel code? Well, because when we raise an interrupt, the CPU doesn't actually know what to do with it. So if you remember from our discussion of how preemption works, when an interrupt is received by the CPU is going to start running the interrupt handler, whose address it knows of because it's stored in the CPU's trap table. And similarly speaking, if we receive a software exception, which is things like division by the zero and an illegal instruction, we are also going to have the CPU end up running an exception handler whose address is in the trap table. Now on MIPS, as I mentioned last class, just to finish our recap here, we did talk about how that on MIPS, interrupts and exceptions are all considered to be exceptions, and interrupt is just a kind of exception on MIPS. There is an advantage to this. It means that you only have to have one exception handler, and the CPU only needs to know one address. But that means that your operating system is going to have to do a little bit more work to try to figure out, okay, is this an interrupt or an exception? And then which interrupt handler am I going to need to call based on that? All right, so before we get into the new content, I forgot we need to finish up a sample problem from last class. So let's go over here. And our sample problem, of course, was proc fork. Now we took up part A last class. Part B, however, we did not do. So I'm just going to make it nice and big here. Start up OneNote. Don't know why OneNote was closed. So I'm not going to draw lines this time. So what we have here is a process that's going to call fork 3 times. And we want you to draw what's known as a process tree that shows you how these processes are created and what the parent-child relationships between them would be. So let's start at the top, and the names I'm assigning to these processes are completely arbitrary, so don't worry if you have different names. The only thing that matters is the edges and the general shape. So I'm going to start with proc A, and that is our parent. And proc A calls fork. So that's fork B. When it calls that, it creates a new proc. Now remember that both proc A and B return from fork, which means both of these processes are going to call the second fork. I'm going to do this in different colors. Make it a little more visible. Again, the names don't matter so much. There we go. Now, what this means here is that both process A and process B forked a new process, which means process A is going to return from the second fork. Process B is going to return from the second fork. But so are processes C and D. So we have 4 processes returning from fork C, which means 4 processes are going to call fork D. Again, we're just going to name them kind of arbitrarily. There we go. So what you end up having here is that each of the 4 processes, A, B, C, and D, all ended up calling the third fork, which creates 4 new processes, and now all 8 processes are going to return from the third fork and then return. So that's a lot of fun. Now, if you're sitting at home and you want to do something fun to get accustomed to working with processes, you might remember in an earlier episode that I discussed that you should try to create a thread fork bomb using P threads. Well, now what I want you to try to do on your own time is to create a process fork bomb. Now, these ones are really fun. So with the thread fork bomb, it's one process with an exponentially increasing number of threads. And the threads are being created at rates faster than they terminate. This, if you open up top, you'll see one process is using an exponential number of resources, and it's fairly easy to terminate. A little harder to find, easy to terminate. Process fork bomb, on the other hand, that's a nasty one. So what you do with a process fork bomb is you're going to want to be spawning processes at a rate faster than they are terminating. Now, if you open up top, what's really cool is that you'll see like 1 billion of these processes all with the same name. But good luck in terminating it, because the processes are spawning at a rate and terminating at a rate faster than you can actually get a handle on them. So that's always usually results for me, and if you get a process fork bomb, you got to reset the computer. Now, if you want to be particularly nasty, which you do, and I'm saying this from experience, is you write one of these process fork bombs and you put it in like the Windows boot file so that when it boots, it actually boots the bomb. And that is how you implement a very, very basic single machine denial of service attack. Is you're essentially consuming 100% of the resources on a particular machine. And of course, then if you want to get into the network side of this, you've just got to spread this to the world. Now, obviously, this is one of the easiest and most oldest forms of denial of services. But it's fun stuff. And it is kind of fun to watch it. So do try to implement a process fork bomb. I actually think OS 161 has one in its user code just as an example, but try to do one on your native machine. Whatever you do, though, please do not run this on the school server. They will get very, very angry with you, and you could possibly lose your account. So this is just something for your own experience. All right, then. So then, back to discussing how are we going to deal with the fact that our user programs can't access the kernel. We've mentioned a couple times now that there's really only two ways that you have to make kernel code run, and that is to either fire a hardware interrupt or raise an exception. And we talked about interrupts and we talked about exceptions, and we've mentioned the fact that on MIPS, specifically, both interrupts and exceptions are both considered exceptions. So these are all of the exception types on our R3000. We've got EXIRQ, which is going to be a true interrupt. Now, one weird, quirky thing you'll note, and if you've ever played around with older Windows and the device drivers, you'll note that interrupts are always referred to as IRQs. I don't know why interrupt is short formed to IRQ. It just is. So there you go. Interrupt is IRQ. All right. Now, some of these exception types you're going to become more and more familiar with as we move through the next few assignments, because they're going to be the bane of your existence. In particular, TLB miss on store and TLB miss on load. Those are going to be two exceptions that you're going to hate. I will post details about how to debug with those, but those are essentially telling you that you have a segmentation fault in your code. And I can tell you how to interpret the results so you can figure out where in your code is that segmentation fault. And if you're sitting there wondering, where is Valgrind to help me find my memory errors, we do not have Valgrind for OS 161. So you're kind of on your own here. However, the exception I want to point out to you, the one that we are actually going to make use of, is EX6. This is a system exception number 8, the syscall exception. Whenever we want our user program to force the kernel to do something, we can't raise an interrupt because that's actually what the hardware is going to do. And we want to differentiate between hardware and software. So what we're going to do is we're going to raise a system call exception. And there is a special instruction called syscall that you can do to do that. So there it is right there. It's syscall. You'll note that on other processors, there are similar ones. Actually, on x86, it's also syscall. It's a very common one. And you'll note it doesn't take any arguments at all. This is actually a problem because there are many different kinds of things we might ask the kernel to do. For example, if I'm downloading something on BitTorrent, then I might have a system call to save data to a file. But if I am watching a movie in VLC, then I'm going to want to be reading data from a file. Those are two very different system calls. And so I need to be able to tell the kernel when I raise the syscall exception, which of those two tasks do I want it to do? So we're going to need to be able to pass some arguments. Now, how we're going to do that is by using some registers. And we already know which registers that we have access to for exactly this purpose. For example, by our register conventions, we know that registers A0 through A3 are used for function arguments. And we know that registers V0 and V1 are used for return values. So we're going to make use of these particular registers for this job. Now we're going to change things a little teeny bit here. So into register V0, we are going to put a special code that tells the kernel which task we're asking it to do. For example, if I load 0 into register V0, then I'm asking the kernel to do a fork. Then into registers A0 through A3, I would put any arguments to my system call that I wanted to raise, noting that if my function requires more than 4 arguments, then I would have to put those arguments either on the heap or on the stack and then pass the address of those arguments through one of A0 through A3. Now, how do you know which of these codes to use and how do you know what arguments there are? Well, there's this thing called the kernel's application binary interface, the ABI. And this is, generally speaking, some header files which are provided by the kernel to the user application so that they can do things like figure out what codes are available to them for system calls, but also how to interpret error codes as returned by the kernel. This is nothing secret that the kernel is giving out. This is just, if you make these calls with these commands or I give you these error codes, this is how you should interpret them. So I'd like to take this opportunity now to actually show you OS 161's ABI. So let's go over here to a terminal. And I am right now in the kern directory. And what I'm going to do is I'm going to go into include. And inside of the include directory is a subdirectory kern. And here you can actually see this is the kernel's ABI. This is the information that is publicly provided to the user programs so that they can know how to raise system call exceptions. So in particular, I'd like to draw your attention to syscall.h. And if you go to line 50 in syscall.h, you will actually see how we have mapped each of the different system calls that we can raise to a particular numerical code. So if I set v0 to be 0, I'm raising a fork. If I set v0 to be a 2, it's exec v. If I set v0 to be 5, it's get PID. And what you can see going through this list is we've got things associated with virtual memory. So we've got ones for expanding things like the stack and the heap. I've got getting security credentials. I've got things for signals. We've also got some process controls like priorities. We've got things related to file handles. We've got paths. We've got current directories, symbolic links, mounting file systems, getting timestamps, securities and permissions, so metadata for files, getting information about the file system, reading and writing, and so on. We've also got sockets and networking signals, things like getting the time and rebooting the computer. All of those things are system calls. Now you'll note most of them in OS 161 are not actually implemented, and you should also note that a lot of things are actually missing. For example, OS 161 does not have a user level thread library. So we are not able to, at the moment, fork a new thread for a user program, which means from A to A and beyond, all of your user programs will have exactly one thread. Now we're just going to have multiple user programs running at the same time, so keep that in mind. So this is part of the kernel's ABI, and this is information that is not secret. It's what the bare minimum of what our user program needs to know in order to actually create one of these system calls. Now, some other files in here of important use are the errorno.h file. And in this file, this is where you will find all of the different error codes that a system call can return. So for example, enosys means there's no such system call with that particular ID. One you're going to need to use a fair bit is enomem, which means that you ran out of memory. So let's say you tried to fork a new process, but when you tried to create their address space, there wasn't actually any memory left. Then you would need to terminate the process with an enomem to indicate, hey, this failed because there's no memory. There's all kinds of different error codes in here. There we go. All right. So now in that kernel's ABI, you're also going to find the places where you need to put the parameters into your registers. So for example, fork doesn't actually take any arguments, so you don't have to worry about registers A0 through A3, but system calls like wait PID and execv do have arguments, and you're going to need to know whether those arguments are going to be found in A0, A1, A2, or A3, so that when you're in the kernel and you're trying to handle that system call exception that's been raised, you will actually be able to look at the trap frame and you'll get the data out of that particular register, which will give you the argument that you need. Now, so that's how you call the codes. So just to give you an example, what this is going to look like. what you're going to have is you're going to into registers V0, you're going to put your code, and you could use load I as well. And then, because fork actually has no arguments, you just do syscall. So the general format is usually load parameters, load syscall code, and then use the syscall exception to actually raise it. Now, this particular bit of code here is implemented for you. You don't have to do this, so don't worry about that. And all of that code that's done there is a part of what's known as the system call library, which is a user level library that's provided as part of the operating system usually, so that user programs can actually make these calls without having to do it directly in assembly themselves. All right, so this is how this is going to work. Now I'm going to talk about this on this diagram, and then I'm actually going to open up the source code and show you where each of these steps actually happens. So let's say you're the user application. We are running our CPU in an unprivileged mode, and so we're going to say fork a new process. So we call fork, which is a part of the system call library, again, an unprivileged piece of code. The system call library is going to set up our arguments to the system call. It's going to set up the system call code, grabbing whatever necessary code is from the ABI, and then it's going to raise the syscall exception. At the point of the exception being raised, what's going to happen is our CPU is going to switch from being in unprivileged mode to privileged mode, and at which point the CPU can then safely call the exception handler for the kernel. Now, the exception handler in the kernel is then going to create a trap frame because we need to save the state of the running program so the kernel can run some code now and go and actually solve your problem for you. So we've switched into unprivileged mode. We've created the trap frame. And now that we've created the trap frame, we need to figure out what kind of exception was this. Was this an interrupt? Was this a TLB miss? Or was this a system call? And if it was a system call, we're going to call the system call dispatcher to actually figure that what kind of system call it was. And in the system call dispatcher, it will look in register V0 and call the function that corresponds to the code. So in our case, sysfork. Now, how does it return values? So when system fork returns, you'll note that the parent and the child get returned two very different things. The parent gets returned the child's PID, and the child gets returned 0. And how do you return something from the kernel back to the user program? Well, the standard way of doing this is to use registers V0 and A3. And we are going to use V0 to actually store our either error code or our return value. And register A3 is going to have our success or fail code. So that's on the previous slide 19 that details that. Now, why do we need 2 return registers? Why can't we just use 1? Well, what if a system call legitimately returns a negative number and that is successful? How would the user program differentiate that particular call returning a negative number from an error code? And this is actually why functions return 2 things, success or fail, and then an error code. So, or the actual proper return value. Success, again, is going to be 0. So we set up, after we've executed sysfork, we set up our return arguments, and then we are going to return from the exception. We're going to push the trap frame back onto the CPU. We are going to flip from privileged mode back to unprivileged mode. We return then to the system call library, which formats the output and returns it to the user application as necessary. So there are a lot of steps that happen on a system call being raised. A lot of things that happen. And it's even worse than this. because whenever the CPU receives an interrupt or an exception, it actually temporarily disables interrupts. So we're going to disable them until we figure out what kind of exception this actually is. And in the case where we have a system call, we are actually going to re-enable exceptions before we handle the system call. So that means that yes, you can have preemption happen while you're executing fork inside the kernel. And that is something to take into consideration, when you are actually implementing fork. Now there's this little bubble here that says, which is faster? So one of the first programs that I actually wrote as a child was for Commodore 64, and we wrote it in BASIC, and it was, we wanted to print the numbers from 1 to 1,000,000 onto the screen. And the question is, how long does it take for a Commodore 64 to print the numbers from 1 to 1,000,000 onto the screen? And the answer is 12 and a half hours. Yeah, a really long time. Now, obviously, you can do this on your own home computer today, and it shouldn't take you even close to that. It should take you like a minute or less. But this actually gets you starting to think. A print is a system call because you are asking the kernel to display something onto the screen. So that means that you need the kernel to be involved, which means you have a system call. So what's going to be faster? Calling printf in a loop 1,000,000 times, or creating a string that contains the correct output and calling printf once? And this is where, when you're writing code, especially high performance code, you need to start thinking about, is the code I'm writing going to raise system calls? And how could I minimize the number of system calls? Things like malloc can even cause system calls. Not always, but it can. And the reason why a malloc can actually cause a system call exception is because if the program's heap is not big enough to facilitate the malloc request, then we need to actually ask the kernel to give us more heap space. So that's going to result in system call. So you need to be very, very careful with your code if you're trying to write high performance code, because these system call exceptions, as you can clearly see, are actually quite slow. All right. Now, before we talk about slide 21 here, what I want to do is actually show you where all of this is going down inside of OS 161. So let's go back over to my terminal, and I'm actually going to move my tablet aside here. And we are going to get out of the include directory. And we're going to go into the Arch directory. And inside of Arch, we're going to go into MIPS, and then we're going to go into lowcore. Now in this, you'll see exception mips1.exe. This lovely file here is the exception handler. This is where and it's an assembly file. This is where, when the CPU receives an exception, this is going to have the address of the exception handler that's going to cause the trap frame to be executed. So we're going to go down here. Now the particular block is called common exception. There's a lot of jumps to common exception. There it is. Sorry, I jumped ahead to the bottom of common exception. I need to be at the top of common exception. So common exception here, this is what actually runs when the CPU receives an exception. And you don't need to understand this in any kind of great detail. But what's going to happen is, first, we're going to check to see what the status of the CPU is. So we're going to check if at the time of the exception we were in user mode, because if we were in user mode, then we are going to switch to privileged mode. And if we were already in privileged mode when we received the exception, there's no point in switching to privileged mode because we were already there. So that's what the first bit is doing, is checking to see what mode we were in and then switching to the appropriate privilege level. And then what we're going to do is we are going to make some space on our stack. And then we are actually going to store the trap frame. So here we are actually storing the trap frame. So you can see us actually storing all of the registers. You'll note that we're also storing some of the special registers. So if we go down here, these are just the basic registers. But if we keep going down, you'll see AT, you'll see RA. You'll also see low and high. So we are saving everything. Now at that point, we have our state saved. And then what we're going to do is we are going to call right here a function called mipstrap. So all common exception actually does is produce the trap frame and call the actual exception handler. The actual exception handler is mipstrap. And you will find mipstrap in trap.c. And I see some people on Twitch here getting a little bit terrified about there being NOPs. It's assembly. It's a pipelined architecture. You're going to have some NOPs. It's unavoidable. So here we go. This is mipstrap. Now this is regular C code. And one of the things I'd like to point out is that at this point in the code, the interrupts are off. So when the exception got raised, we turned interrupts off. So while we're executing mipstrap, interrupts are still off. While we're saving the trap frame, interrupts were off. So what we're going to do in here is we're going to figure out what kind of exception was raised. And what I notice here is the first thing we do is we check to see, is it an actual interrupt? If it's an actual interrupt, we're going to call the interrupt handler called main bus interrupt, and we're going to leave interrupts off. We're going to let the interrupt handlers handle whether we turn interrupts back on or not. However, if it is not an interrupt, regardless of what other kind of exception it is, we're going to turn interrupts back on, which means that you can be preempted while doing the rest of this work. The next kind of exception, and the one we're interested in, is we're going to look at the system call exceptions. So here you see we've got syscall, and if it is that type, then we're going to call the system call dispatcher, and we're passing to it the address of the trap frame. And we pass the address of the trap frame because the trap frame actually contains all of our parameters and the call code. Okay. So that is common exception, which produces the trap frame and mipstrap. Now we need to look at the system called dispatcher, which is in not Arch MIPS low core, that's in Kern Arch MIPS syscall. And again, this is a C file, which is very nice. It's fairly well documented. And what you can see here is we're going to take the trap frame and we're going to get the call number from register V0. And then we have a big old switch statement based on the call number. And for each of the different kinds of call codes, we are going to call the appropriate internal kernel function to handle that particular system call. And with each of them, we will pass to that function whatever appropriate arguments were stored in the registers A0, A1, A2, A3 that were stored in the trap frame. So there you go. That is the syscall exception handler. Now, at the very bottom of the syscall dispatcher, you'll see us actually setting up the returns from the system call. So if there is an error, then into the V0 register of the trap frame, which is what is going to be restored once we're done handling this exception. So that would be how we return things to the user program. So we put into register V0 the error code if the system call failed, and then into register A3 we put a 1 to indicate failure. Now if this was a successful system call, then into V0 we put the return value, and into A3 we put 0 to indicate success. And then the last little bit of the system call dispatcher, which may seem a little odd, is you'll note that we increment the program counter by 4. And the reason for this is when we raise the exception, we are stopping the program counter from being incremented to the next instruction. That is the one after the syscall code instruction. So if we don't increment the program counter manually, then what's going to happen is when we return from the exception, we'll just keep raising it again and again and again. So to stop us from continuously raising that system call exception, what we're going to do is we're going to manually increment the program counter past that syscall instruction. Keep that in mind because you're going to need it. Now, this syscall dispatcher, once it's done, returns to MIPS trap. MIPS trap is then going to return to common exception. Common exception is then going to restore the trap frame to the CPU, and then it is going to switch the privilege mode back to unprivileged and jump back to the user program that's running. All right. Now, that's all fine and dandy, but we're still missing one piece. Here's the interesting piece that we're missing. The piece we're missing is the fact that we actually have not one stack per thread, but 2 stacks. Now, you might be wondering, why do you need 2 stacks per thread? Well, here's the thing. And every OS handles this slightly differently. Some, it's every thread has 2 stacks. Some have a special kernel stack. Lots of different implementations. OS 161, each thread has its own stack. It's 2 of its own stacks. So every thread has a user application stack, and every thread has its own kernel stack. Why? Well, here's the problem. Let's suppose that every thread had a single stack. In OS 161, our stacks have a maximum size, and believe it or not, there is a maximum size in every other operating system as well. A lot bigger, and they have a lot more room to grow than we do. Our stacks, however, are limited to 48 kilobytes. Let's suppose that we use one stack to store both kernel stack frames and user stack frames. Well, then what's going to happen is you're going to have some user program start exploring that stack, trying to say, hey, can I find any kernel data here? We don't want that to happen. So we want, for security reasons, to keep the kernel's stack frames separate from the user's stack frames. So that's reason number 1. Here's reason number 2. Let's suppose your user program uses 99% of the stack, but never has a stack overflow, and it's completely valid. Okay, then there's an exception, and the kernel starts using your stack. Well, the kernel, its very first stack frame that it puts on there, which is going to be the trap frame, what happens if the trap frame overflows your stack? Then the kernel is going to cause the user program to terminate, even though the user program did nothing wrong. And we don't want the kernel to be able to overflow the user stack and cause the user program to terminate when it never actually should have, because it's done nothing wrong. So we actually like to keep the kernel stack and the user stack separate, which means that we've got to do one extra thing when we raise an exception. So that extra thing is that when we actually raise the exception, you'll note at the top of common exception, after we figure out what mode we've come from, there's actually a bunch of code to find this current thread's user or kernel stack and switch to using the kernel stack. And then the trap frame and all of those stack frames are going to end up going on the kernel stack for that thread, not the user stack. And that's something very important to keep in mind. Now, if you're sitting back and thinking about, well, what about when we did context switches with threads? What stack then are those stack frames going to go onto? And the answer is the kernel stack, always the kernel stack, because we don't have a user level thread library. We only have a kernel thread library, which means thread yield, thread switch, and switch frame are all kernel functions. They can only be executed while we are in kernel privilege mode, which means that they are going to end up going onto our threads kernel stacks. Now, where can you find the address of these kernel stacks? If you look at the thread structure, which is in kern include thread.h, there's a tstack field. That's actually the address of the kernel stack. One other thing I want to mention is that the kernel stack is significantly smaller than the user stack. So the user stack is 48 kilobytes and the kernel stacks are only 4 kilobytes. Now I'm going to skip the next few slides, just for those of you who are following along, simply because we've already shown you this code and I don't see a point in actually showing it to you a second time. Which is going to leave us with our last kind of topic before our big example for threads here. And that's going to be discussing the concept of multiprocessing or multitasking. So obviously, any modern computer has the ability to run multiple processes at the same time. And that means that all of our processes are sharing the available resources, so memory, CPU time, and so on and so forth. And our operating system is going to be responsible for both fairly sharing the CPU and time and resources between all those processes, but also doing the actual management of that. Now, one of the things to keep in mind is that processes don't run. Threads execute, not processes. So realistically, when we're talking about multiprocessing, we're still really just talking about threads and context switches between threads. Except now, instead of context switching between threads of the same program, now we can switch between the threads of different programs. But if you actually look at what that looks like on the stack, it's the same. So just to give you a little example here of what's going to happen. Now, in this particular diagram, so we have a quantum, a scheduling, so a large scheduling quantum. And let's say our scheduling quantum is 30 milliseconds. But we've set our timer not to go off after every 30 milliseconds, but instead let's let each process, we're going to set the timer to go off after every 10 milliseconds. So then what we're going to do is process A is running, process B is not running. So process A's thread, there's a timer interrupt. So we go into the kernel mode, we check to see if the quantum has expired. It hasn't. So we go back to running. Quantum expire, or the timer goes off again. Quantum is still not expired. We go back to running. And finally, on the third timer interrupt, the quantum has expired. And so we're going to get process A's thread is going to be switched to another thread. And we just so happen to choose a thread from process B. And then the process repeats. Now, we can do this in a few different ways, and I've seen it implemented in several different ways. One way that you could do it is you could treat every thread of every process the same, and they all get the same scheduling quantum. Another thing that I've seen is people say, okay, well, we'll let processes have larger quantums than the individual threads. So we will, let's say, the processes each get 30 or 50 milliseconds to run, and the threads inside of that process will let each of those threads have 10 milliseconds each. So that would give us the ability to let multiple threads within a given process get some time. Again, there are many, many different ways to implement this. This is just one particular example. All right, so I'd like to now go through this little example here about drawing the stacks for what happens when you have multiple processes running and system calls and timer interrupts. So this is the remainder of the slide deck. So remember again that our user processes are going to run in an unprivileged mode, and our kernel runs in privileged mode. And we've got a bunch of user processes here. We're only going to deal with 2 of them though. So our user process here, process 1, which I guess I've also called process A, has a user stack, and we are running user application code. Now, while it's doing its work, it decides it's going to call fork. So our process 1 is going to call fork. So fork is a system call function. And so we're going to call the library, which is also a user program. And the system call library function is going to load 0 into register V0 and then raise the system call exception. Again, this is happening in user space. At the point that syscall is raised, so that's going to cause that exception, the CPU is going to call common exception, and it knows the address for common exception to be this here. So we're going to switch from executing in unprivileged mode to now we're executing in privileged mode, and we're also going to switch from using our user stack to our kernel stack. And now we're actually going to start executing common exception, which is actually the process of saving the trap frame. So there you go. We've saved our trap frame. And now what we're going to do is we're going to call MIPS trap, because now that the context is saved, now we can actually consider, okay, what kind of exception was this? So we're going to call MIPS trap. And inside of MIPS trap, we're going to figure out, again, what kind of exception it was and call the appropriate dispatcher for that kind of exception. Now, remember that if it is an interrupt, we call main bus interrupt, and interrupt stay off. We're going to let the interrupt handlers deal with that. But if it is not an interrupt, then we're going to turn our interrupts back on. This is going to come into play in a minute. So MIPS trap realizes that this is actually a system call. And so it calls the syscall dispatcher. The syscall dispatcher looks at register V0 stored in the trap frame and notices that would be a fork. And so it calls sysfork. And so the fork is actually executed by the kernel. Now, what happens if, while we are executing sysfork, the timer goes off? Okay. So what's going to happen now is that we get a trap frame because we had an interrupt fired and interrupts are on. So we get a trap frame. Anytime you have any kind of interrupt or any kind of exception, you get a trap frame. And immediately following the trap frame, you're going to get a MIPS trap. The trap frame is common exception, saving and restoring the state of the running thread and also deciding whether we were in unprivileged mode, making that switch to privileged mode and all of that business. So upon receiving the timer interrupt, after sysfork on the kernel, we get a trap frame followed by a MIPS trap. And then the MIPS trap realizes this is a timer interrupt, or an actual interrupt, so it calls main bus interrupt. And main bus interrupt says this was the clock. So we call the interrupt handler for the clock. It is then going to be the scheduling quantum expired. And so the clock's interrupt handler is actually going to call thread yield, and then thread yield calls thread switch, and thread switch calls switch frame. So there's all that business from earlier episodes. All right, that switch frame, if you remember, the first thing it does is it saves the remainder of the context of the calling thread, and then it's going to restore part of the context, the callee save registers, for the new thread that's going to run. And then the last thing that switch frame does as you're executing it as part of process one is that it's going to pop the switch frame off of the stack of the new thread. So we are now returning from switch frame and thread switch. We return to thread yield. Thread yield returns to the interrupt handler, and this again is the new thread of the new process. That returns to its interrupt handler, which just returns to main bus interrupt. Main bus simply returns, then we restore the trap frame. Finally, we're going to switch back from using the kernel stack to the user stack. We're going to switch from privileged mode to unprivileged mode, and now we end up with proc2 goes back to its user application running as normal. And then we have a question. Can you overflow the 4K kernel stack if you get unlucky with context switches, or is there a way to watch out or prevent that from happening? In OS 161, no. Context. Yes, that can happen in OS 161. There is, to the best of my knowledge, no prevention for that from happening. Is that likely to happen in OS 161? No. This is actually part of the balance of writing your kernel code. Your kernel code needs to be as fast and quick and dirty as possible, because you don't want to take execution time away from the user program, because that's going to make the user believe that their program is stalled. And as part of it, that usually means that things like sysfork and saving and storing files need to happen as quickly as possible. The other thing that's true here is that when you're implementing an operating system, you need to select scheduling quantums that make sense. So you need to have the timer interrupts and the scheduling quantums happen at such a rate that you actually manage to make some progress towards your goal before you get the next context switch. Because if your context switches are happening too close together and then you're going to spend all of your time executing the context switch code and none of the time actually executing the real code. So it's kind of a balancing act. I'm sure that this still happens. Like, I'm sure that kernels still encounter this, especially if you've got a device driver that does something particular bad, because device drivers are usually a part of the kernel and run in privileged mode, which means there is the potential for them to cause bad things to happen. And that does happen. If you've ever had a blue screen of death in Windows, a lot of the time it's a device driver that's caused the blue screen of death. And the same is actually true for things like Linux. When you get a kernel panic, a lot of the time it actually comes down to device drivers. So is it possible? Yes. OS 161 does not prevent against kernel stack overflows, to the best of my knowledge. I'm not sure about things like Linux and Windows, if they're preventing it or if they just grow the kernel stack. But there are general mechanisms in place such that you shouldn't have this happen unless something exceptional is going on. All right. We'll talk a lot more about device drivers when we get to the device driver section, which is probably one of my favorite sections, but I could probably say that about every section. All right, so let's go back in time and let's see what would happen if you didn't have that timer interrupt and the context switch. So if you didn't have the timer interrupt and the context switch, so you've got the system fork here, we're executing sysfork, and then we return from sysfork because we created the new process, and then the syscall is going to need to set up the return values for the fork. So you see here it executes this error bit or the success bit based on whether we succeeded or failed with our fork. Let's say we succeeded. This is just copied right from syscall.c. So we put the return value in register V0 and success in A3. And then we increment our program counter. We return from syscall to MIPS trap. And then from MIPS trap, we're going to return to common exception. Common exception is then going to restore the trap frame. And then it's going to switch from using the kernel stack back to the user stack. And then the last thing it does is it jumps. You'll see this jump, which is going to be going back to running the user program. And then you see this RFE. That stands for return from exception. And that's going to switch our CPU back into unprivileged mode so that our kernel code can actually run. Or not our kernel code, our user program can actually run again. There we go. All right, so one last thing about that example before I talk about this particular slide here is traditionally this is where I would say, oh, in your midterm, make sure you have all of these stack diagrams memorized because we always ask them. We do always ask them on midterms and exams. You don't have a midterm, which... I mean, it's good for you because I think exams are incredibly stressful situations, which may not necessarily be measures of how well do you know the material, but they're also stressful for us because we have to mark them and it takes a lot of time and effort to mark them. But that being said, you will have quizzes on this. They're just auto-marked by, of course, Learn. And even though you don't have to write these out by hand, do anticipate that we have questions about these stack diagrams here. So make sure you go over this in some pretty good details. And again, I know you don't have a midterm, but maybe I'll post the traditional midterm review slides just to give you some extra sample problems to look at to make sure that you're understanding the material. All right. The last slide then, which actually used to be its own separate module at the very end of the course, but we decided to merge it in here because this is where it belongs, is the concept of interprocess communication. So I talked earlier about the fact, in the last episode, episode 9, that processes are isolated from each other because we don't want what one process is doing to impact another process. I don't want processes to be able to cause race conditions for each other and things like that. But it still makes sense for processes to be able to communicate with each other. For example, a very old project that I worked on almost 10 years ago now, what we had set up was we wanted to do what's known as real-time onset pre-visualization for motion capture. A bunch of mumbo-jumbo words, I realize that. The idea is if you have movies like Avatar or pretty much any kind of science fiction or fantasy action movie today uses motion capture. That is actors in these tight black suits covered in these little tiny silver balls or patterns. And they are sitting in this room with hundreds of cameras, and the cameras are watching the actors act out their scene, and then we take their body motion and we apply it to a digital character. Now, the problem, of course, with this, I promise you this is related to OS. The problem with this is that the actors aren't actually able to see their character or the virtual world that they're acting in. And so the performance may not be as good as it would be with traditional film capture. So we wanted to build a system where the actors were actually able to see themselves in the virtual world and interact with the virtual world as they were acting in the fake world. So we needed to take the motion capture data, which is in one process, and we needed it to go into a video game. And we used Unreal 3 to do all of our rendering. So the actors and the director were actually able to see a high quality real-time rendering of the animated characters while the actors were doing their acting. And the actors can actually wear a little camera headset so they can see through the eyes of the virtual character as well. So it's kind of a cool system. So we needed to get data from the mocap process into the Unreal process. How do you do that? Because these are two very separate programs. And Unreal at that time was not designed for this task. It was a lot of fun. So this is what inter-process communication is for. Inter-process communication is mechanisms by which we can get data from one process into another process. Now, the first thing that I did was I actually used this second from last option here is shared memory. Now, what this is the operating system is going to set up a region of memory that both processes can access. And then processes can write to it and the other process can read from it. That was the first way I did it. This has problems with race conditions. How do you know it's safe to read and write at the same time? The other problems with shared memory, of course, is that this is assuming that your motion capture software is actually running on the same system as your the Unreal Engine was running. And the computers at the time, that wasn't necessarily a good idea because that's some really powerful software. And we were running it on laptops. I'm going to be honest with you, not really a good idea. So then you have to ask, well, what are some of the other options that we could have used for two processes to communicate with each other other than shared memory? Well, a file could be used, but that kind of suffers from the same problem as shared memory. How do you know when it's safe for one process to read and the other process to write? And it also restricts both processes to being on the same machine at the same time. So this is doable to let two processes communicate with each other, but maybe not the best option. Then you have things like pipes and message passing. These are special system calls and parts of the operating system. The kernel is offering you a utility to let processes talk with each other, where the OS is actually going to provide some kind of shared queue, and it's going to do some kind of management of the data on that queue. So message passing and pipes are actually a common strategy. What we ended up using, and what I like to use, is actually sockets. So what did I use? I used the network. And the reason why I used the network for the IPC in this particular case was we didn't want to have the restriction that the mocap software was running on the same computer as Unreal was. We wanted also the ability, since our mocap volume is actually really small, we wanted the ability to have multiple motion capture volumes all dumping data and in different locations around the world, all dumping data to the visualization at the same time. So we decided to go for a network approach, and you can use the network to actually do IPC. So that's another cool way of doing it. So there are lots and lots and lots of different ways for you to actually have two processes communicate with each other. The major considerations you have to take in mind, though, are how am I going to handle race conditions where two processes are trying to read and write data at the same time? And you should also be asking yourself questions like, does it make sense to permit these processes to communicate with each other if they're not running on the same computer? All right. Someone is posting on Twitch about VR acting classes. If that is something that interests you, please let me know. Because certainly I am aware of VR and mocap acting classes out there, although under the current pandemic situation, I believe they've all been shut down. But if I have a list of names of people interested in this, I'm happy to post dates for such events whenever they become available. Of course, these will be happening in Toronto. Totally unrelated to us, though. All right, so that is actually the end of the processes module. You now have everything that you need to do both assignments A2A and A2B. And on that note, on our next episode, episode 11, I'm actually going to go over how to do assignment A2A. If you want to get started, there is already from the fall of 2019, the episode, I think it's the Halloween episode, has how to do A2A. But I will go over that briefly again in our next episode, and we will also start our new topic, which is virtual memory, which will help complete the isolation of one process from another and processes from the actual kernel. So we will see you next week.
Okay, high performance, low cost. That's what I need. Something with plenty of power. Huh? That runs popular software. But most importantly, the processor inside has to be affordable so I can save money on whatever PC I buy.
Life is full of difficult decisions. This is not one of them. Cyrix, first-class performance without all the cost.